Everyone, welcome to your Chemistry 1212 Rates of Chemical Reactions lab lecture. Let's go ahead and jump right in. So chemical reactions can occur at very different rates. You can compare the slow oxidation of iron into iron oxide, which is just rust, what you see here, with the nearly instantaneous reaction of burning hydrogen gas once the initial spark is given. So they are very different rates. Some variables that affect the rate of a reaction are temperature, concentration, and whether there's actually a catalyst present. Okay, we have a trivia here. If you want to write these down and turn these in when you come in for this lab, if you get them correct, I'll give you some bonus points. Number one, what is a catalyst? Number two, what does an increase in temperature do to the energy? Number three, what is rust a product of? Number four, what is the rate of a given reaction gauged by? Number five, what do reaction orders characterize? Number six, what is investigated in this particular experiment we're going to do? And number seven, what characterizes how the rate is affected by each reactant concentration? All right, right back into it. So the addition of a catalyst lowers the activation energy, the minimum energy required for a reaction to take place, by orienting the molecules for favorable interactions. Now, an increase in concentration increases the probability of a productive collision. Any of these changes may speed up a reaction. You can see the difference between like hot water and cold water here on the slide. The rate of a given reaction is gauged by either the consumption of the starting materials, which is reactants, or the formation of products. This measurement of concentration is related to time such that when the concentration, which is X, or a reactant, is monitored with this formula. N is the coefficient of X in this balanced equation. You're going to see the negative sign in the equation since X has been defined as reactant and therefore is being consumed, which means it has a decrease in concentration during this entire reaction. Now, the initial rate of a reaction is investigated because it's easy to determine initial concentrations of reactants. And an equation can be written that relates reaction rate to the initial concentrations of all your reactants. Your rate may or may not, depending on the concentration of every species in the system. And your reaction orders characterize how the rate is affected by each reactant concentration. Consider action involving reactants X, Y, and Z. And that's what we're showing you here, okay? The lowercase letters represent coefficients in the balanced equations, okay? The uppercase, obviously, you can see here, are going to be your reactants. So let's kind of look at it this way. If the rate does not depend on the concentration of Z at all, it is zero order with respect to Z, okay? In other words, in the rate expression, its exponent is going to be zero. That's what you see right here on the slide. If the rate doubles every time the concentration of Y is doubled, the reaction is first order with respect to Y. If doubling the concentration of X leads to a quadrupling of the rate, it is second order with respect to X. The rate expression for a reaction can only be determined experimentally, and the rate equation for this example would be this equation where K is the rate constant for the reaction at a given temperature. The overall order of a reaction is the summation of the orders of all the components. So we're saying, like, for this example, the overall order is going to be 2 plus 1 plus 0. Okay, 2 plus 1 plus 0. The order of each component must be determined experimentally. This is done by changing the concentration of only one component at a time and then noting the change in the rate. Now, once the order of every component is known, then the rate is constant, or K, and it can be determined using concentration information from one of the trials. Once your K is determined, along with the order of the reaction, the rate expression can be used to calculate or predict the rate with the different concentrations. The reaction that's going to be investigated is an oxidation reduction, okay, with peroxydisulfide ion, which is your S2O8 2 negative, and the iod ion. The iod is oxidized to iodine, and the peroxydisulfate is reduced to the sulfate ion. Starch is the indicator for the reaction, and it's going to turn blue in the presence of iodine. Now, since the starch will turn blue instantly in the presence of iodine, we would not be able to determine the rate with just these two reactants in the solution with the indicator. We would see a blue color change instantly as soon as the first molecules of iodine would form, and we would not be able to gather any time-dependent date. Therefore, we're going to have to add something to slow the appearance of the blue color. We're going to add the ion thiosulfate, which undergoes the following reaction with iodine. So this is your reaction with your iodine, okay? All right, now at this time, the excess iodine is going to complex the starch indicator, turning the solution blue. The data you collect is going to be the time delay between the addition of the thiosulfate and the change in color. After some time, can't tell you exactly how much, it might be different for everybody, all the peroxydisulfate is going to be consumed and more iodine is going to be produced. Now, the excess iodine will complex with the starch indicator, turning the solution blue. 10 this way, you will indirectly measure the disappearance of the peroxydisulfate ion through the pathway shown here, and you're going to be able to determine the rate of that reaction. Okay. Now, you're going to start with a relatively small amount of thiosulfate in solution compared with the initial amounts of peroxydisulfate and iodide. When the 2.0 molecules is consumed with iodine, meaning when it turns blue, 1.0 times 10 to the negative 4 moles of peroxydisulfate is going to have reacted with iodide because of the stoichiometry of the reactions. You're going to record the time from the start of the reaction and then add another 2.0 times 10 to the negative 4 moles of thiosulfate, which is just a milliliter. The solution is going to become colorless again as thiosulfate reacts with iodine. When the blue color appears, you're going to record the time. You're going to continue this 3 more times for a total of 5 data points. You'll go through this procedure a total of 3 times with different initial concentrations of iodide and peroxydisulfate as indicated in your table A in your handout, but with the same amount of thiosulfate each time. Because of the relatively small number of moles of peroxydisulfate consumed during each time interval, you should be in the linear initial portion of the rate curve for the duration of the reaction investigated, which is what you're going to see. You're going to plot the concentration of peroxydisulfate remaining as a function of time. Now, since peroxydisulfate is a species monitored during the experiment and its coefficient is 1, like you see right here. Okay, so the value of N is equal, the value of N is equal to 1, and that means that the initial rate of the reaction is the negative of the slope of the line that you plotted, okay? Negative the slope of the line that you plotted. This is just kind of something for you to look at to see what we're talking about. The values of the rate of the reaction from each trial are going to be used to determine the order and the rate constant for the reaction of the peroxydisulfate with iodine. Now, notice how the slope of the graph is going to be negative because the concentration of the peroxydisulfate is decreasing. However, the rate of the reaction is positive. So this is just so you can see. And remember, we're using at least 2 sig figs, okay? That is all we have for your rates of reactions lab lecture. If you're having issues, please reach out and have fun doing this lab. It's a fun lab. Bye, you guys.